Yeah, thank you for the introduction. I'm H.R.Schmidtke. Sarah Coelho is also here, I think. And I'm going to talk about analogous semantics and yeah, scales and hedges. Oh, no. I had tried this. Oh, my. Okay. Okay, let me start right ahead. So analogous semantics, it's good to remember Peirce, the semiotic triangle. We have, if we have an object in the world, let's say a car, then the symbol is the word car, for instance, and then the interpretant is what a human being has in mind, and this is obviously what we are mostly interested in. Now, the ability to imagine, to actually form a sort of image-like model may be critical for pro-social behaviors. There is a lot of evidence for that, in particular in the area of empathy. The ability to share another's feelings and emotions is critical probably for compassion and distress. In contrast to affective empathy, there is also cognitive empathy that is making inferences about others' mental states, the ability to perceive their intentions, motivations, and expectations. And if you look at pathologies that present with impairment in empathy, this becomes very clear. Psychopaths have preserved cognitive empathy, but low affective empathy, leading to antisocial behavior. And people with autism show deficits in cognitive empathy, but have their affective empathy intact, leading to normal morality. So this imagination state seems to be key for good decision making. It's vital to know what the consequences mean, so the semantics. So for instance, should we invest in climate change action or economic growth? Let me give you an example of what the system that I present does with this problem. And it has an analogous semantics. So reading this description, it will generate this analogous model, so directly from the text. And so here we have two nations. Nation one is growing with respect to wealth, and we can see this starting to appear here. If nation two stops growing, its wealth will stay the same. But if nation two does not stop growing, nation one's wealth will become lower in comparison to that of nation two. If neither of them stop growing, millions will lose their lives at some later time. So here you can see we have the situation where our nation one has stopped growing, and we can see what happens here. How does nation two decide? They continue. No, they also stop growing here, and we can switch to the health dimension, and we see million people. The millions are at their normal health here. So the next option, now again, we go here through this initialization step. So we read the text. Nation one is growing with respect to wealth currently, and then stops growing. But this time, nation two did not stop growing. So it is more wealthy in the end. But again, if we look at the health dimension, everybody is still healthy here. Now we go on. We have more cases to cover that turn out here, just logically from the logic. So now we have a model where we don't stop growing. You see E2, the situation at time at the later time is higher in wealth. So the maximum is here, the minimum is there, and both have taken the risky path. Nation 2 also has increased its growth. Millions have died as a result. A very drastic depiction of what happened that could cause, could represent the shock of this high risk situation. And then there is, we have another option that's also contained in this text. And so again, our nation 1 does not stop growing. And so we have E0, E1, E2. But in this case, nation 2 stopped growing. And we can see, again, the millions are saved due to nation 2, in this case, making the right decision. So this is a kind of system, and we want to extract this simple semantics, analogous semantics, just out of the description, the logical description. And okay. So what we usually have are set theoretical semantics for mathematical logic. These originated in the 19th century. Before that, there was no really formal logic. In the 20th century, also people were looking to alternatives to set theory as a basis for the foundation of logic, and in particular, Lezhnyevsky's protothetic has to be highlighted, and it uses a mereological foundation of logic. Mereology is a flat foundational relation part of between individuals of the same level, instead of the hierarchical element of, where you have an element of a set. So one is an element, the other one is a set containing it, which creates hierarchies. It had influential followers such as Tarski. Its advantages, in particular for continuous domains, for instance, time and space, you can avoid continuity, second-order logics. In terms of mathematical structures, mereology describes a lattice or semi-lattice structure, which is a generalization of Boolean algebra, so that fits well with Boolean algebra as a logical theory. And also in the 20th century, there was a focus on equivalences between logics and mathematical theories in general. So, for instance, close relationships between intuitionistic logic, certain modal logics, description logics, and also fuzzy logic were found, and all those as based on lattices and semi-lattices. Also, computational structures, directed acyclic graphs, this class includes trees, belong to this category. Generally, any partial order gives rise to a lattice structure. So this is a very relevant category for our domain. Now, context logic, the logic I would like to present and that is used in the system is a cognitively motivated logic with a lattice semantics. Now, analogous semantics, if you don't know context logic, maybe you know fuzzy logic invented by Zade. And here we can infer from a statement like this shoe is red to a degree of 90%, we can reconstruct the color of the shoe from the statement with a degree. So there is truth and meaning in an intuitive sense of correspondence with reality. And fuzzy control systems are an example of how useful this is. But the meaning of an entire text, as the one we've seen, is still just a numerical truth value. So context logic can go beyond that. The second component is the reasoner for this system. It is a vector symbolic architecture. Vector symbolic architectures are an abstract distributed model of cognition. They implement an intentional pointer association semantics for relations and anything else. The advantage is that everything is of the same type, whether it's an input image or an output symbol. All we have is an activation pattern representable by a vector. But there is no analogous semantics in vector symbolic architectures. So I developed a specialized VSA for logical reasoning with full analogous semantics for a complex context logic formula, such as the description that I've shown you. So what is context logic? Context logic is a two-layered logic. And on the lowest layer, we have context terms. So the current context and an outside context and atomic context terms. You have the complement, you have the intersection of two contexts, and you have the sum of two contexts. If you have a context and another context, you can form statements about their relation. So C is a subcontext of D. So this is a context formula because it's a formula about contexts. Now you can use all the familiar logical operators, negation, conjunction, quantifiers. So everything looks very simple. I've studied conventional semantics for this system. So there is a set theoretical semantics, a possible world semantics, and the first order logic axiomatization, which I'll show here. And the most recent one, a category theoretical semantics, is probably the most elegant one. Semantics, if we look at the semantics, basically all we need is that this operator, this core relation, this one relation we have is a partial order. So it's reflexive. Every context is a subcontext of itself. It's anti-symmetric. So if alpha is a subcontext of beta and beta is a subcontext of alpha, then they share the same subcontexts. And it's transitive. If alpha is a subcontext of beta and beta is a subcontext of gamma, alpha is a subcontext of gamma. And we can relate this relation subcontext to implication. So if beta is a subcontext of gamma, then all its subcontexts are subcontexts of gamma. This allows us to move any complex context terms operator to the right-hand side, so we can easily axiomatize the meaning of intersection and intersection and sum and complement. So the intersection between two contexts, if the current context is in the intersection of alpha and beta, it is in alpha and in beta. Now the sum is more complex. If the current context is in the sum of alpha and beta, then for any of its subcontexts, there is a subcontext that is in alpha or in beta. Yeah, so the current context does not need to lie in alpha or completely in beta, but the parts of its parts, so to speak. Now the complement is related to this symbol for outside, and with empty domains excluded, to negation, to. So the current context is outside the complement of alpha if alpha is outside, is in, subcontext. So we can also immediately derive relations. The converse is very helpful to specify opposites, north to south, small to tall, and so on. We have equality. We can specify overlap as the intersection of alpha and beta is not outside, then they overlap within the current context. And we also have non-empty subcontext derived from this. Now comes the interesting part. So using the conjunctive term operator, any arbitrary number of further partial order relations can be constructed. This is a basic property of lattice structures, without the need for introducing relational symbols as a distinct class. This allows us to understand certain contexts, like in the example, wealth or temporal before, as relational or dimensional contexts. These are just contexts. This allows us to analyze any relation in terms of this one singular relation. Not only partial orders, which I'll come next, but also to general non-partial order relations, which we can describe in terms of a graph or tuple construction. A wide range of relations, relevant relations in reasoning, are partial orders. For instance, spatial part of, north of, temporal relations, and so on. The transitivity of partial orders is fundamental in many domains. Often, that's what we are interested in, this transitivity inference. And if I have alpha and some relational context X, then the intersection of alpha with X is part of alpha. So this is reflexive, gives us reflexivity. Anti-symmetry, if alpha, if the intersection of alpha and X, or the X aspect of alpha is in beta, then, and the X aspect of beta is in alpha, then the two aspects are identical. And transitivity too. If alpha, if the X aspect of alpha is a subcontext of beta, and the X aspect of beta is a subcontext of gamma, then alpha, the X aspect of alpha is a subcontext of gamma. All these follows via this simple property. So the if we have the X aspect of alpha part subcontext of beta, this holds if and only if the X aspect of alpha is subcontext of the X aspect of beta. So you see the symmetry here. And the second part here is true because trivially the X aspect of alpha is a subcontext of X. Yeah, so that's how we get this. And then we can define a simple contextualization syntax as a shorthand for this. And this already brings us very close to the conventional way in which we write relations in first order logic. We can say that this conventional syntax is a further abbreviation of this simplified syntax where we have the comma instead of the relation. So this statement is within the most fundamental expressive level. This is just an atomic formula. context logic. And we already have the reasoning backbone for any partial order for free. That is only without requiring any further axiomatization. So how far can we get here? And this is the list I have in the paper, where the trolley problem is discussed. And so we have north, south, east, west, large, small, left, right, side, up, down, to, from, the ing form, and the before, after, move, and on the side of verbs, moving, running, going, continue, recover, drive, pull, heal, harm, kill, give, receive. So a lot of things we can do just with this framework and needing no further axiomatization. So here you can see how we can construct 15 temporal relations simply on the basis of two partial orders. But we can also create general relations, and we do this by describing basically their graph. So, for instance, the instance of relation is not a partial order because of that hierarchical difference between elements and sets. And the way we do this is to say, okay, there is an edge that is part of the graph, and all those are just contexts. I'm just calling it an edge so we can more easily picture that. And then the intersection between the edge and the object is in the argument 1 apart, and the intersection with the end of the arrow, and the intersection with the class, and the edge is in the argument, is in the A2 position, the second argument, the tip of the edge. So formally, this construction is called.
There's just 4 minutes left now. Sorry to interrupt you.
So formally, this construction is called a tuple generator, and we can construct arbitrary relations this way, which are in particular those which are not partial orders. So again, we can see that we can say that this more conventional relation statement in predicate logic is instance of alpha beta, can be seen as an abbreviation, syntactic sugar, for this more complex statement, that there is an edge and so on. So now, do these arise naturally in normal language? Yes, in the form of action verbs. The Davidsonian event parameter does exactly what we're doing here. We have a tuple generator construction there, or you could also say a hypergraph edge with different roles. So not only the tip of the edge, but there is a subject, an object, and so on. So here is an example of how we can analyze an intransitive verb with an adverbial prepositional phrase like Tom goes down the street. We have Tom is the subject, and then we have this aspect here. So the outer event is en, and now we have the new event en plus 1. Tom is the subject of en plus 1, and goes does not have any dimension. But down the street, we have down here is a dimension. So we have a relation between en and en plus 1. En plus 1 is down from en, partial order, and the object is the street. And likewise, we can model the physician heals the patient as the healing increasing the patient's health. So we are at what you've seen in the beginning there. So we have derived the conventional syntax of predicate expressions, demonstrating that these can be considered internally complex constructions. We gain the advantage of reducing the number of axioms required, and we have shown that a context logic does not replace conventional predicate logic, but slices it up. And if we have an analogous semantics for CLA, CL0, CL1, we thus also have an analogous semantics for first order logic. So how can we derive that? We can implement a context logic reasoner using a vector symbolic architecture by interpreting the vectors logically with bitwise logical operations, and for the intersection or for the sum, and negation here for the complement. So assume we have random binary vectors A, B of long length, let's say 10,000 bits. Then we get with the bitwise AND operation, we get a focus operation. We focus on those parts of A that are also in B with the intersection of A and B. We also get a filter operation with a negation. So if we have the negation of A and B, that means we filter out those parts from B that are in A. And we can implement the subcontext relation by looking at all the positions and checking whether AI is smaller or equal to BI, or equivalently for all positions AI, and not BI is 0, or likewise the negation of it is 1. Now, if we have a formula phi, a knowledge base, like A is north of B and B is north of C, and we encode it in this manner here, we can also ask queries like, is A north of C? And we can check that by checking whether negating the knowledge base and then or Q is the 1 vector. So really classical. But we get more. We get analogous representations. So if we have phi and x, that is a focus of the information phi has about the object or relation x. If we do that for an object A and a relation N, we get information about the N aspect of A. And in particular, if we have our knowledge base again, and we look at the vectors phi and N and A, and N and B and N and C, we see that with phi, with this formula, we remove, set to 0, all positions I, where phi I and Ni and Ai is 1 and Bi is 0, and all portions where Bi is 1 and Ci is 0 with this formula. So in other words, all positions where phi I, Ni, Ci is 1 have phi I, Ni, Bi as 1 and phi I, Ni, Ai as 1. And all positions where phi I, Ni, Bi are 1 also have phi I, Ni, Ai is 1. So in essence, if we count the number of ones, we can see that phi and N and A is larger or equal to phi and N and B, and that again is larger or equal to phi and N and C. And now you know how we got those coordinates in the demo. So generalizing phi and N and X represents the number of ones in phi and N and X numerically, the N aspect of X, or an N coordinate. We generate from the text coordinates. So of course, there's a lot more to say here. So how do we reduce interference? We do that by filtering out other relations from the query. How do we rotate mirror images? There's a paper about that. So you need that for root instructions, for instance. And how can we build the CL1, CL0 reasoning on top of this? I haven't said anything about this here, but it's in the demo, so you've seen it. And what it does, it's using conventional first-order logic tableau reasoning, and each branch yields a separate image. You've seen we had 4 distinct images where I checked what happens in this or this or this situation. So those are the branches of the tableau. Okay, origin of the gap in conventional first-order logic semantics is the focus on general relations instead of looking at partial orders as an interesting case from a cognitive systems perspective, very natural. Context logic is a mature logical language with a unique image semantics, so we get a unique image for a formula. And first order logic can be understood in terms of CL. The activation bit vector machine gives us conventional classical reasoning and complex formula grounding and grounded reasoning, and also for first order logic. So we've seen the system, if it can be shocked at all, it can be shocked by the extreme risk situation in the game of chicken scenario in the demo. And we've also seen scales. So for instance, the scale wealth, and on the other hand, the maximally catastrophic situation, which would be tied to existential threat. And we can imagine this is the first step to getting empathy into a machine. Yeah, thank you.